Yeah, that's what I feel.
Dude, salty.
Alrighty, good morning, everyone. So, just a reminder we talked about yesterday at the end, that was thin film interference. So again, thin film interference happens when we have three different mediums, where the second medium, of course, is thin, hence the thin film. But anyways, each one has their own index refraction. So again, here we get light, which is then reflected off of the top layer, and then some that is transmitted down and then reflects off of the second and then transmitted back through then to the first medium. And then in the thin film is the interference between those two reflected rays, which is what we call ray 1 and then ray 2. So in this case, I think I called it yesterday L, and switch notation. I think I call it T today for thickness instead of length, but still the same thing. Now again, here we have to pay attention to how these things actually occur. So basically meaning, again, if I go from a low index refraction to a high index refraction, I get a phase change. And if I go from a high index refraction to a low index refraction, there is no phase change. So you can write that down. So if I go from high to low, then there is no phase change. But if I go from low to high, then there is a phase change. Here, again, I have to pay attention to the total number of phase changes I have. If I have one phase change and not another phase change, so I have one overall, in this case, then my constructive and destructive interference is switched. So in this case, then what would usually be destructive interference becomes constructive interference, because again, the two are out of phase, so I have to overcome that fact to put them back into phase with each other. And if I have no phase changes or two phase changes, then I have the regular type of thing that we had before, which is constructive interference stays the same. Destructive interference stays the same. And then here, again, what I care about though is the wavelength inside of the second medium, because this is exactly where the path length difference is occurring, only within inside of the second medium, which means that the wavelength is changed by the index refraction of the second medium. Okay, so this is what we call thin film interference. What's up?
What's the 0 or 2?
So 0 means the total number of phase changes. So if I have 0 or 2 total phase changes, then I have this version. If I have only one phase change, then I have this version.
And that happens like high to low, low to high is the index of refraction.
Correct. So it's how the index of refractions line up. So first I have to look at how this one compares to this one, and then how this one compares to this one. So again, if I go from a low to a high here, I get a phase change. But if I go from a high to a low here, then I get no phase change. So for example, let's say that, I don't know, this was glass, this was air, and then this was water. So in this case, this would be 1, this would be 1.5, and then this would be 1.33. So in this case, I'd go from a low to a high, which means I would have a phase change in R1. But in this case, going from 1.5 to 1.33, that would not give me a phase change. So in this case, I'd have no phase change on this one, which means I have one overall phase change. So that'd give me this scenario here. But if I had like an example we did yesterday, which was air to acetone to glass. In that case, this was 1, this was then 1.25, this was 1.5. In that case, there was what? This was low to high and then low to high. So I had two phase changes, which brought me back to this one. So I just have to pay attention to what each one of the two are actually doing. So how these guys relate to each other. So again, this is 0 or 2 phase changes, and then simply 1 phase change. So we did one example yesterday. Let's do one more example today. And then I got some group assignments for you to kind of start working on. Great. So this one says that light is incident perpendicularly, again, almost perpendicularly, on a thin film layer of material 2, which has an index refraction of 1.6, of thickness 285 nanometers, that lies between materials and 1, equal to 1.55, index refraction, and then 3, which is 1.33. If the waves interfere maximally, which in this case means I have maximum constructive interference, what is the wavelength of the wave in the visible light spectrum? Okay, so let's look at this. So this is my example. So again, here what it's telling me is I have, here are my mediums. Okay, so this is my thickness. This is N1, this is N2, and this is N3. N2 we were told was 1.6, N1 was 1.55, and then N3 was 1.3. Sorry. 33. So water. 1.33. Good. So what it tells me then is that what the light ray which comes in here and then reflects off here. So this is ray 1, and then again the one that gets transmitted, reflected, and then transmitted, ray 2. We're told here that this thing interferes completely constructively. Yeah. And I'm also told that the thickness of this was 285 nanometers. So my thickness is 285 nanometers. So basically from here, what we want to know then is what is the wavelength of the original wave which is coming in. So I want to know what is this wavelength. But not only what's the wavelength, but what's the wavelength within the visible spectrum. So we have to remind ourselves that the visible spectrum consists of wavelengths between 400 nanometers out to about 700 nanometers. So this is our visible spectrum. So basically, when we're solving for this, we want to find a wavelength that is somewhere in this range. So just a reminder of something. So good. So first things first, to know which one I have to use, if I have to use 0 or 2 or 1, I have to look at this and determine how many different phase shifts do I have. So let's go and do that. So in this case, I'm going for ray 1. I'm going from 1.55 index refraction to 1.6 index refraction. So I'm going from a low index refraction to a high index refraction. So does that give me a phase change or not? Yes. So here I know that this one is phase changed. I have a phase change. But for the second ray, I'm going from what, 1.6 down to 1.33. So in this case, I'm going from high to low. So if I go from high to low, does that give me a phase change or not? Good. No. So in this case, I have no phase change, which means overall I have one total number of phase changes, which tells me that my change in length then, which is equal to twice the thickness, is then going to be equal to n plus 1/2 times lambda divided by n2 for constructive interference. And then n times lambda divided by n2 for then destructive interference. Now again, our problem told us that we have constructive interference, which means we're going to simply use the top one. What's up?
Are we always going to be told if it's constructive or destructive, or are we going to have to figure that out?
Let's see here. So sometimes you'll have to figure that out based off of do you see it or not. So if you see it, it's constructive interference. If you don't see it, then it's destructive interference. So for example, if I told you that what I saw here was yellow light, for example, if I told you that this was yellow that you see, then in that case, it would be constructive interference because you're seeing the yellow light at that stage. So everything else is destructively interfering. The other one that is constructively interfering would be yellow. So yeah, so that's the only time I wouldn't tell you if it was flat out constructive or destructive interference. Okay, so if I gave you, for example, it was a color, and it's implied in that case, then that's constructive interference, so that's what you're seeing.
Would the wording of this being in the visible spectrum count?
You mean in that type of problem?
Yeah, because
Well, the only way I would see yellow is if it was a visible spectrum anyways.
okay.
Otherwise, it would have to be something like infrared or X-ray or ultraviolet or something like that. But yeah. So in this case, if I say you're seeing a color, it's implied that it's somewhere in the visible spectrum. Okay. So good. So from here, we know we're using the first one. So in this case, we're going to say our change in length then, which is twice the thickness, then is going to be equal to n plus 1/2 times the wavelength divided by n2, because we have constructive interference. From here, what we want is the wavelength. So let's go ahead and solve this for the wavelength. So what we're going to do is multiply by n2 and divide by n plus 1/2. So in this case, I'm going to get twice the thickness times n2 divided by n plus 1/2 is all equal to the wavelength. Now, similar to the one that we did yesterday, we don't know what the n values is, which means we don't know if it was the first time it happened, or the second time it happened, or the third time it happened, or etc. So we don't know what the n value is. So in this case, what we're going to have to do is plug in different n values to find the wavelength, and then the first wavelength that shows up within inside of the visible spectrum corresponds then to the correct n value. Again, our parameter is that we have to have it within inside of the visible spectrum. So let's go ahead and do that. So let's start off with n is equal to 0, and then we'll do n is equal to 1, and then n is equal to 2, and then eventually just stop when we get to the visible spectrum. So let's do that. So if I do n is equal to 0, in this case, then I get 4 times the thickness times n2, then is equal to the wavelength. Because in this case, I get 0 plus a half, so the 2 moves to the top, so that becomes 4. Look at my number, what I get in this case then is this works out to be 1,824 nanometers. Is that in the visible spectrum? Oh, good. So in this case, then I have to work at n is equal to 1. So if I do n is equal to 1, this is then going to become what, 3 halves. So it'll move to the top. So it's going to become 4 up here and 3 divided by the bottom. So in this case, my wavelength then is going to be 4 times the thickness times n2, all divided by 3. Plug in that. What I find in this case then is this works out to be about 608 nanometers. Is that within inside of the visible spectrum? Yes. So in this case, you know the wavelength in this case then has to correspond to n is equal to 1, which would be 608 nanometers. Okay, what's up there?
Since we're finding an answer in nanometers, we need to convert T to nanometers and then back to.
No, in this case, we can keep T in nanometers the whole time, and we can just find the wavelength in nanometers. That's fine. What's up, Omar?
Wait, where did the plus 1/2 go?
Where did the what?
The plus 1/2 go? One plus 1/2 in the denominator there. Where'd it go?
Where to go with? So which case? For this one?
So like you have 4T n2 is equal to the wavelength. I don't know how you got that.
Oh, good. So let's write all that up. So in this case, if I have n is equal to 0, this then gives me 2 times t times n2 divided by 1/2 is n equal to lambda. Okay? But this is a 1 over, which means the 2 moves to the top, which then gives me this expression. Okay? For this one, I then have 2t times n2 divided by 3/2. The same thing, this is a 1 over, which means the 2 moves to the top, which then gives me this expression. So it was there. I just did a whole bunch of steps of algebra, just the confusion. I like it. Everybody's okay? So that's it. Thin film interference, not too bad, nice and easy. So again, either you're going to be told, for example, what Derek was asking, either it's constructive interference or it's destructive interference, or that the color you see is something like yellow, and then you just have to, most cases I'm not going to tell you what the n value is, you just have parameters which can either tell you n value, or you would have to infer the n value by, for example, this means where it happened. Was this the first time it happened? So n is equal to 0 means the first time it happened was at this frequency. Next time is going to be at this frequency, and then etc. What's up there?
The n value is just node, right?
The n value is what?
The n value is a node.
Well, not really node because it's not a standing wave. It's more of, you can think of, it's the first time you would see that particular interference. You can kind of think of it that way. So it's more of this is the first time you see it versus the second time you see it versus the third time you see it, etc. Okay. So let's do some group assignments. I have 2 for you today. First one's nice and easy. This is just a Snell's law problem. So first one says we have a light beam strikes a 2 centimeter thick piece of plastic with an index of refraction of 1.62 at an angle of 45 degrees, which means that this angle here is 45 degrees. Remember, our angle is always the angle relative to the normal. Even though 45 is the same as the horizontal in this case, but it's always relative to the normal. The plastic is then on top of a 3 centimeter thick piece of glass whose index of refraction in this case we're taking as 1.47. So what then is the distance d that the light emerges after it has passed through the glass? So basically what's going to happen here is light's going to come in, get refracted down into the plastic, then it's going to be refracted then into the glass, and then eventually be refracted back into air. So this is air here, and this is air here. And what I want to know in this case then is simply what's this distance here? So what's the distance between where it entered into the plastic, right? Yeah, versus, plastic. versus where it exits the glass. So here, basically, all we're going to do is apply Snell's law twice, and then from Snell's law, just going to do some geometry, and then from the geometry, you'll then determine what's this distance here. So in this case, easiest thing to do here would be find this distance here, call that like D1, find this distance here, call that D2, add the two distances together, that's the total distance. Based off of Snell's law, we're going to use Snell's law here and Snell's law here. Second one then says, this is a thin film interference question. This says light is incident perpendicularly on a thin layer of material 2, which is 1.6 index refraction. Thickness 400 nanometers that lies between materials index refraction of 2 for the first material and then 1.33 for the third material. The waves, the rays in this case, R1 and R2 interfere maximally, which means again we have constructive interference. So what is the wavelength of the wave, again, within inside of the visible spectrum of light? So basically exactly the same question that we did, but with different index refractions, which means I probably have different number of phase changes. So you've got to go through and figure out what phase that you're having, et cetera. Same thing here, all you're gonna do is start off with different n values. Until you find something which is within the visible spectrum, which you're gonna need to have to be somewhere between 400 and 700 nanometers. Which here tells you that it should be about 533. You should find. So I'll let you work on those. Depending on how long it takes you to do those, we might start some new stuff. Otherwise, we'll call it a day. See how things go. After this, we'll start looking at mirrors, making images from reflections. Idea why they keep this roof flat. Some wood there, but. Oh, the jacker. Yeah. Probably just don't. That could be true too. I don't know if hey, you never know. You really want to hide.
Oh, I don't
Is there
know.
anything,
What's that?
is there anything in the cabinets?
I looked, no.
Other universities, yeah. Pretty much all day at home.
Well, it depends. I mean, this does say it's like their media room. So. But there's nothing in here that I would call media. Oh, sorry. Even performance plan. I was media room.
It's not even me.
There's like a
Human
performance. It's a way.
Right. So, I mean, there's a hydrotherapy here, but that's fun. Big old oven. But if you could steal that thing, I'd give you props for that. I don't think you can get it to the door. Right. But I think you'd have to know what's here. Otherwise, it's probably headed through. Yeah, exactly. So that's thing ever disappeared, I'm pretty sure. It's like, what's up there? Right? The 45, don't just find it. Exactly. Yep, that's it. Yep. And you know, n error is 1. Yeah, just take arc cosine or arc sine of both sides. Yep. Yep. Oh, the second one? Let's see. And you counted all your total numbers? Correct. Yes. So in that case, we're using that one. And you start off at n is equal to 0. 400. Got 640. Okay. Yes, that's definitely. It could be I made a math mistake. It's always possible. You never know with me. But you're right. You're always going from high to low. Oh, good question. Well, technically, they're both correct. You have 600 and 400. Assuming you can use your calculator for it. Yeah. So the first one you got 600. Yes. So 640 corresponds to orange. 14 red. So it's 4 something. So that's violet. So, yeah, so technically they both. I guess in this case you're not report full. You could theoretically have. But I don't.
Well, the setup's correct.
Yeah, that's right. So it's just so in this case it's gonna be 800 times 6. So that's your first one, right? Right, for the second.
Yeah.
Yeah, so it should be 640. And the other one should have been multiplied by 2. Yeah, 4.6.666. Yeah. Oh, you're right. What's up?
So I have to like,
No. So in this case, what you're finding is the new angle. Right. So basically, what Snell's law now is telling you is this angle here. But you already know the length of this side, so you're saying, well, tangent of this angle then is equal to this divided by this. Now find that. Because you know that. That's it. Nice and easy. Yeah, so in my usual customary, it looks like this number is wrong. So this should be either 640 or 426 or 427, something like that, depending on how you round it. But so in this case, there's actually 2 invisible light spectrums. Apparently, I still don't know how to use it. Oh, so in this case, it's saying it interferes maximally, so it's implied in that wording that it's constructive. But if I wrote down an example, for example, I would make it more clear that it's constructive. Okay. Yes. Yes. That's it. So, well, this is the critical one. So we're not using this one. So what we're using is just regular stuff. So you're just using this. So in this case, you know, N1 is air, for the plastic one on top. So then you have N1 times sine of 5 equal to 2, and 2 in this case is 6, 2 times sine of blank. And then you're looking for blank. I'm sorry,
That's these are.
construct. What did the other one say?
Oh. What do you mean?
But we're taking it as construct. Yeah, it's kind of ambiguous. What did it say in the last one?
What last one?
The example.
Oh, in the class, it said,
Said something like that, right? Interferes maximally.
I thought you said you just do it because it was like,
yeah, because it was
I
like,
could see it.
No. So what I'm saying is, if I told you you saw yellow, then you would know it was interfere construct. So that was a subsequent question. Different. That could make sense if it was destructive. That's why I had that. Just go with construct.
So that number works if it's destructive.
I don't know. I'd have to.
I'll try it.
Okay. Almost gonna do it. Yeah, 'cause last time it also said interfere maximally, which we took as constructive answers, which gave us the answer. So mimicking what we did here, that it should do the same. But let's go ahead and try. So who is with destructive? Do that one and see what you get. Sure. That's a good one. Well, we all. Well, minimally would basically just mean, it doesn't interfere at all. Which doesn't really make sense. But here, yeah, it's ambiguous because you can interfere maximally both constructively and destructively. So in that case, if this was like on an exam, I would just flat out say it constructively or destructively. Or I would say you see yellow, which means that again, they are constructively inferior because you're actually seeing. Everything else then would be destructively. But yeah. So interfere maximally on the previous problem when we did it as an example, we took that as constructive interference. But in this case, Omar's going to tell us what number gets destructive. Because if you do it for constructive interference, you should get 640 or 426. What'd you get, Omar?
Right. The strength of N2.
That's your value for.
Yep.
You just.
Yep.
And N2 is this.
Yeah. The 1.6. So it's going to be 2 times 1.6 times 4 times 1.6. Divided by,
I get 512.
so you got 512 for the n equals 2. Good, so no matter what, we're not getting. What's up? Yeah, so that's what Omar got, if you do destructive interference. Yes, it was 512. So I don't know where I got that number, 533. But that was,
You know,
well, for constructive interference, you get 640 or 426. Those are both visible light spectrums that work. No, so in your case, this is destructive because you have to, again, look at the total number of phase changes. Okay. Well, in this case, there's none phase changes, right? Because you're going from, so if you look what's happening, so it's saying that you're going from 2 down to 1.6, which means you're going from high to low. High to low gives you something. And then you're going from 1.6 down to 1.33, which means you're also going from high to low, which means there's no phase change. So remember, we have to look first at, right, so here N1 was equal to 2, not to 1.
Okay. I thought that was like, it would.
Yeah, so that's what this one is saying. So your material number 1 is index refraction of 2.
Oh, I see what it's saying now. I thought that was like a list of materials.
Gotcha.
The way I read it, I thought it was like
From air. Gotcha. Okay. Gotcha. No, in this case, it's coming from whatever has index refraction of 2. Which, offhand, I don't know. Okay, Paige.
Yeah, so would there ever be a case of, so it's a thin wall and
Yep.
whatever that we use and one.
No.
Or and three, I guess.
And again, the reason for that is because the pathing difference is occurring within inside of the second week, which means we only care about what is the frequency of the wave within inside of the second medium.
Yeah.
Since by the time we interfere where we see it, which is within inside of the first medium, the wave is of the same. So the only thing we care about is that pathing difference. That only occurs within inside of the second. It's just there to tell us that if there's a case.
yeah, I mean, one thing.
I just like seeing the diagrams. It makes more sense.
The drawing will always be the same. Yeah. So the only thing that's going to be different is basically the total number of phase changes as well as what you're looking for constructive versus destructive. That's basically it. So that's the only thing that's going to be different in these types of problems.
It's 1.33 instead of,
Oh, did I?
yeah, instead of,
It's possible.
yeah.
It's possible I was a little crazy.
And you find that in your head, it's pretty cool.
I also did this like 4 years ago, so I can't tell you what I essentially did. So. Actually, it might even been longer than that.
So do you find this problem every year? Like, say it's wrong?
Pretty much, and then I say I'm gonna go back and fix it, and then I never do.
So how are the lab practicals looking? Started.
I haven't, because there's one more group that has to go today. So when I grade all of them. So. It's just a lot easier to grade someone when you're in the mindset to grade all of them. Well, that way you're also consistent. So I might grade all the other ones and then go back and grade now the ones from today, but I don't remember exactly the number of points I gave for certain things, and then I'm not consistently grading it the same. So it's just easier to do them all at once.
So when it says interferes maximum, is that constructive?
Yeah, we're going constructive.
Okay.
That's right. But again, on an exam or something like that, I would just say constructively interfere or destructively, just to get rid of that ambiguity. Or again, I would say, you see the color yellow, which again means that it's constructive. Again, just to alleviate all the ambiguity.
Given a color, wouldn't that give us the?
Yeah, you can guess the wavelength.
I'm sorry.
You can guess the wavelength.
Are we always gonna find wavelength with this?
Well, no, because the example we did yesterday was finding the thickness of it.
Okay.
So we knew the wavelength. So in this case, I told you it was yellow that you saw, and now it's telling you the wavelength. But it also doesn't tell you the end value, and it doesn't tell you the thickness. So in that case, you would have to know other things. So for example, this is when knowing if it's the first time or the second time or the third time that you see it, would it correspond to different end values. So an example of that would be an example I've given on an exam before. I'll kind of draw it up for you. But it was something that kind of did this. There was a material here, and then there was another one that kind of changed height as you went through.
I don't know.
And then basically I said, okay, in this region it was like dark, and then after this you see like yellow here, then you see like red here, blue, et cetera, and then eventually over here you see yellow again, and then red again, and then blue again. And then from this you're determining then the end value. So since this is the first time you're seeing yellow, this would correspond to n is equal to 0. This would be your n is equal to 0. This would be your n is equal to 1. Somewhere out here you would get yellow again. So this would be your n is equal to 2, and et cetera. But each one of these then would have a different thickness, and then you're solving for the thickness of that material. Okay. That kind of makes sense.
You'll never have more than 3 layers for thin film, right?
Not for this class. Not for this class. But theoretically, you could. You could have. So as long as each layer is pretty thin, you could still have multiple amount of layers. Now, the only problem with that though is every time it goes through a layer, because we have to remember, even in this case, not all the light is going in this direction. So some of the light here is being reflected here, some of the light is being reflected here, some of the light here is being reflected here, which means every time it hits a boundary, part of it is reflected, part of it is transmitted, which means the intensity is always decreasing. So if I had multiple amount of layers, like in this case, say I have basically 4 layers, right? I have one here, one here, one here, one here. So our typical thin film is between these two, but I could also get a type of thin film interference from this one as well. Again, the problem here is that the intensity has reduced so much that the amount of interference that you're going to get because the intensity is so low, you probably need to look at this anyway. So.
I heard in class the other day, you did like an individual 3 and then 4. Like we did.
Oh yeah, yes. Well, that was determining what the thickness was. That's right.
How do we have that? Is n the layers or?
No. So n is basically. So if I go again back to this picture of this group for.
My next question is gonna be, what if you ask like what wavelength of light is in the visible spectrum, but there's more than one? Like,
Well, that's what happens in this problem. So you just record it. So again, so here, you can think of that as basically the first time you see this interference happen. Corresponding. So here this would be the first time, the second time, the third time, and then et cetera. So actually, it turns out in this problem, we do constructive interference. There are actually 2 different frequencies.
Yeah.
There's 640 and then there's 426.
Yeah.
So one of them is basically orange, red, and then the other one is violet. Yep. So here. So oh, why is it there? Because again, the path-length difference only occurs within inside of the second medium, which means that inside of the second medium, the wavelength has changed by a factor of the index required. And the reason for that is because, as we mentioned on Monday, the frequency stays the same regardless of what medium it actually is, because we talked about that a long time. So, but since the velocity changes, the frequency stays the same, that means the wavelength has to change. And by the amount that the wavelength changes is just the index refraction, which you can prove to yourself by simply saying the velocity is equal to lambda times the wavelength. But you know, the velocity is c divided by n, so that means wavelength has to change by n as well. So that's where the n comes from. So that's where index refraction n comes from. Okay.
So we're just. No, I did. Yes, that's new.
Well, it's construct interference, but again, you have to pay attention to how many phase shifts do you have. So you have to look at how N1 compares to N2, how N2 compares to N3 to determine the total number of phase shifts. So you can't use any of those equations until you know the total number of phase shifts.
But in this case, we don't have any space.
I'm sorry?
In this case, we don't have any space.
There's no phase shifts in this case, correct? Because you're always going from high to low. Correct. Yes. So once you know that, then you just use the appropriate equation and then you can find the.
And then just plug in.
You just plug in different n values until you find something in the physical spectrum. Anybody still working on it? Sure. Yeah, so
You're right. I never got to say my goodbye.
Alright, so here is the illusion.
I make some fun. I said, I never got to say my goodbyes today on the last test. Because he won't. Actually, was he? No, he was in the laptop. The high state.
So this one is not. I said, this one.
Yeah.
I wish you know. So here, no.
You might have what?
Unlike the previous question,
I think he's just an E1.
All right, are we okay? All right, so we got about 7 minutes left, so we'll talk a little bit about image formation from mirrors. So the next thing we're going to start looking at is image formation from mirrors. So basically, all we're going to do is we're going to bounce light off of mirrors, and then we want to see what type of image do I get by bouncing light off of these particular mirrors. And the first type of mirror we're going to look at is what's known as a plane mirror. So a plane mirror is simply a mirror whose radius of curvature is equal to infinity. Okay, so this is what we call a plane mirror. So what happens in this case? So let's say here's my plane mirror. So here's my mirror. Great. Here's my mirror. And let's say I'm going to put something in front of the mirror. Let's say I put, this is my object. Okay, so this is going to be my object. This object has a height to it. Let's call this height h. And then this is going to be some distance away from the mirror itself. And let's call that a distance of s. So s in this case is then going to be equal to my object distance.
What is R equal or what is R?
Oh, r is the radius of curvature of the mirror itself. So this is my radius of curvature. That'll be more apparent when we get to the next portion, which is spherical mirrors.
Kind of like what we did in the last lab.
Kind of. That was with lenses. We'll get there after we do mirrors, but it's the same idea. Okay. It turns out to be exactly the same expressions as well, which makes this nice and easy. So good. So we want to know what type of image am I going to create from this particular type of object. So let's say I have some rays. So my first ray I'm going to say goes from here. So it's going to go from here, hit the mirror at some stage. So hits the mirror. We know from the law of reflections that if this thing comes at an angle, say theta 1, where this is my ray 1, then this thing has to reflect off at exactly the same angle at which it came in. So this thing's going to reflect off at an angle such as this. So it's going to be my reflected ray. Again, this is going to be at exactly the same angle of theta 1. Simultaneously, this is going to give off another ray of light. So let's draw that one gray. So let's say this is this ray. It's going to come in, hit the mirror at this stage. So here again, What I know is this is going to be at some angle. Let's call that theta 2. Theta 2. And then this guy then is going to reflect off at exactly the same angle. Guys here, so something like this. So that this angle here is also going to be theta 2. So our eye is going to be somewhere out here looking at these reflected rays, and it's going to try to interpret where this actual object is. So what I'm going to see is I'm going to ray trace these guys backwards to find out where the origin of these rays actually came from. Remember, as we talked about yesterday, our eyes are pretty stupid and wants to watch everything move in a straight line, which means since these lines are actually diverging away from each other, if I ray trace them backwards, they're eventually going to connect at some point. So they're going to converge back onto each other. So I'm going to ray trace this guy backwards. Draw a straight line. There we go. I'm going to ray trace this one backwards. And then where these lines actually intercept each other is then the location of the image. So this is then going to be my image. So in the mirror itself, the image then is formed at this particular location. So let's make some more nomenclature. So let's say this distance here from the mirror to the position of the image is called S, which is what we call the image distance. And then this thing is going to have a height to it. The height then is what we're going to call H prime, which is equal to the image height. Now, basically what we can do is we can do some geometry. I'm not going to bother basically doing that, but I'm going to talk to you about it real quick. But basically, if I extend this normal line in this direction here, and this normal line in this direction here, we can easily convince ourselves that this angle here is the same as theta 1. This angle here then is the same as theta 2. Because by the law of reflections, we know that this angle here has to be the same as this one has to be the same as this one, which means that this triangle here and this triangle here is exactly the same as this triangle here and this triangle here, which should then convince us that what? This distance of S and this distance of S prime is actually exactly the same. This distance of H and H prime are also exactly the same. So what happens for plane mirrors then is that S, the object distance, then equals then negative S prime, which is then our image distance. And then the height H is simply equal to H prime. So basically what happens is with a plane mirror, we get boring things that happen. So as long as my radius of curvature is infinite, meaning this thing is simply a plane, what happens then is that the size of the object is exactly equal to the size of the image I see within inside of the mirror. And the distance my object is away from the front of the mirror is exactly the same as the distance that the image is away from the front of it. It's just on the back side. Now, some things to point out about this image. This image is what we call a virtual image. And this is called an upright image or non-inverted. So what does virtual image mean? So what virtual image means is, notice what the light is actually doing. So this thing is somehow creating light. Now we haven't talked about how it actually creates light. It can either create light itself. For example, the light bulb here that's blinding me as I look at it for some stupid reason. But this thing creates light either by itself, in this case, or it reflects light. Most of the things I see is actually because it reflects light. I see Omar and Ruth and everybody in this classroom because you're reflecting light. You are creating light, but it's outside of my visible spectrum. I can't actually see it, so I'm only seeing you because you're reflecting light. So in this case, this could be either one. It could be reflection of light or generation of light. It doesn't matter. We're exactly the same way. But basically, this thing is creating light. This light then bounces off and goes into our eye in this direction. Right? It's originally here, comes in this case, hits the mirror, and then bounces off in this case. But the image location I see is behind the mirror itself. Which means that this is what we call a virtual image. What a virtual image is if I put my piece of paper exactly here where I see this image, it will not be formed on this piece of paper because no light is actually passing through the actual image itself. This is what we call a virtual image. As opposed to a real image, which means that it would be formed at a location where the light actually passes through the image itself. For example, when you guys did the lenses lab, all of those were real images because the light was actually passing through the image itself. That's how we saw it. We put that piece of paper there, it was formed on top of the piece of paper, so that's what we call a real image. So a virtual image is an image that's created with no real light passing through. So no light passes through. Is what we call a virtual image. Upright just means it has the same orientation as the object itself. So in this case, object is pointing upward, image is also pointing upward. This is what we call. So that's it. This is for, as far as plane mirrors are concerned, this is all we care about. So starting off tomorrow, I'll give you another group of assignments corresponding to plane mirrors, and then from there, we'll start talking about more interesting cases, which are spherical mirrors. Have a good rest of your day. I'll see everybody tomorrow. Bye. Or- Yeah.
So we're only looking at.
Correct. Well, we're looking at, so the phase change occurred between the reflected light and the incoming. So the incoming light will always stay in the same phase because it doesn't change phase going from one medium to another. But it does change phase when it is being reflected. So that means that in a way, yes, we're looking at the difference between the two outgoing rays.
Okay, so we're just looking at the difference in the boundaries,
Correct.
right?
That's-
Okay.
Exactly.
That makes a lot more sense.
Good.
Because I was looking at it and I was like, well, okay, that makes sense for incoming light, but the outgoing light does not. But we're not even concerned about that. We're just looking at the difference at the boundary.
Correct.
Okay.
Because a difference in the boundary will then cause the reflection to be either in phase or out of phase.
Okay.
Exactly.
Okay.
So all you care about is how does N1 compare to N2, and then how does N2 compare to N2.
Gotcha.
That's it. And then we don't care about what happened with the.
That's perfect. All right.
Okay.
Thank you. That makes much more sense.
Good. Good.
And this is a great example of how